Hello YouTube. In this video I'm going to keep talking about graphing functions. First of all, why should we be interested in graphing functions? And the answer is that they're very important for understanding almost all of science and engineering. The university textbooks are full of equations, and it's very helpful to be able to have an understanding of the characteristics of these equations. So an ability to graph rather complicated functions will help in the STEM fields tremendously. And I haven't seen this material in any other place, so I'd like to present it to you and hope that it's of some assistance. I'd like to explain about this function, sine cubed pi x squared over x squared plus 1. Now this looks pretty complicated, but we'll just break it down one piece at a time. This is three different modifications of the sine function. The first is that the sine function is cubed. The second one is that the argument to the sine function is x squared. And the third modification is that we're dividing everything by x squared plus 1. So I think this last one is the easiest to understand. In the previous video, we've already talked about this function, 1 over x squared plus 1. And this has a shape of a small round hill with a height of 1, and the origin is the center of the hill. So when we see sine pi x divided by x squared plus 1, I think it's very helpful to think of this as sine pi x times 1 over x squared plus 1. And we already know what this one looks like. So in order to draw this function, we're going to draw the upper envelope and the lower envelope, which is the negative of this. For any function to draw the negative of it, it just means flipping it from the top to the bottom. So the dashed line is the lower envelope and the solid line is the upper envelope, and between these two lines our sine function is just going to go up and down, because the sine function has a maximum at 1 and a minimum at -1. The maximum value is 1, and it will come up to the upper envelope. When the minimum value is -1, it will touch the lower envelope. So, as we can see here, the sine function just oscillates between the upper and the lower envelope. We put the pi in here just to make it easier to draw. We know that the normal sign will come back to 0 at pi. When we put the pi in here, then when x is only 1, after multiplying it times pi, this passes a value of pi onto the sine function, which makes it come back to 0. So this function will be 0 at all the integers. This is 1, 2, and 3. And the amplitude will become smaller and smaller as it oscillates between this upper and lower envelope. This in electronics is called amplitude modulation. The second change that we need to understand to do our original problem is cubing the sine. So let's look at what the function x cubed does. X cubed takes 0 and leaves it at 0. And it also takes 1 and leaves it at 1. And it takes -1 and leaves it at -1. If we make a small table to explain that, -1 stays where it is, 0 stays where it is, and 1 stays where it is. Now the numbers in between there will become smaller, like 0.5, 1/2. When we cube that, we get 1/8. which is 0.125. So when we draw a picture of this, these points are unchanged, and this point will be pulled down towards the axis. Now we're going to apply this to the sine function. Here's a regular sine function, going from a minimum of -1 up to a maximum of +1. All of these points will be unchanged, and the places where it crosses the axis, where it's 0, is also unchanged by cubing it. So I drew circles for these unchanging points, and in between there, it's going to level out momentarily when it crosses the x-axis. The regular sine function is crossing the x-axis in more or less a straight line. After cubing it, it will be leveling out momentarily. So the net effect of cubing the sine function is to make all of the peaks and all of the valleys narrower, and also have this momentary stopping each time it crosses the axis. Now we're going to combine those first two changes. Remember, the original problem was sine cubed pi x squared. So I'm ignoring that x squared for now, and we'll just think about what cubing it does together with putting it in an envelope. So this is the function with a minimum of -1 and a maximum of 1 that we're putting in the envelope of 1 over x squared plus 1. So we just draw the upper and the lower envelopes as dotted lines, and then this same curve goes in here. And it's like this one. It's becoming 0 at x equals 1, 2, 3, and at the negative integers also. In between those, the peaks are getting narrower, the little valleys are getting narrower, and it's also stopping momentarily each time we cross the x-axis. Now let's think about what the x squared part does to this. The original sine pi x function became 0 whenever x was an integer value. So this function is also going to become 0 whenever x squared is an integer value. Now x squared becomes an integer value at, of course, 0, at 1, and at the square root of 2, at the square root of 3, and 2, which is the square root of 4. So this curve will be symmetrical on the left and right side, because when we compute something in here, the first thing it's doing is multiplying x times itself. So if x is a negative number, it just becomes something positive. So it's left and right symmetrical. And it's crossing 0 at every square root of an integer value, which it will do more and more frequently. Between 1 and 2, the square root of 4, we have the square root of 2, about 1.4, and the square root of 3 is about 1.7. And between 2 and 3, which is the square root of 9, there's going to be 5 crossings. So this function is still oscillating between -1 and +1. It's just getting faster and faster. Now let's put it in an envelope and draw it. So the same function, sine pi x squared, now divided by x squared plus 1. So we draw the upper and the lower envelope, and then draw this function inside there, only going up to the envelopes. And it's getting faster and faster as we go. And when we want to do the cube in this, I don't have a picture for it, but it will be basically the same picture. The modifications to this is that the peaks will be narrower, and the little valleys will be narrower, and also each time it crosses zero, it's going to momentarily level off. One other feature of this curve that I didn't mention yet is that it starts off slowly, and that is because x squared starts off slowly. Remember, x squared is a parabola, and that's what's being fed in here. So this is starting off flat and round like a parabola is. Alright, here's another interesting function that we can use in constructing our own kinds of shapes that we want to build. 10 to the x. Not necessarily 10, but 2 to the x or 100 to the x, whatever. It's all the same shape. It just changes how fast it becomes big or small. So the graph of 10 to the x is very close to 0 for negative numbers and is extremely large for positive numbers. At 0, the value is 1, and it quickly grows after that. So when we make a graph of just 10 to the x, we'll try it out on these values. Negative 2, it's 1/100th. At negative 1, it's 1/10th. At 0, it's 1. At 1, it's already up to 10, and at 2, it's up to 100. Now, 10 to the minus x will be, where this is 100, this is 100. Because this minus x will get rid of the minus and the 2. So at negative 2, the value will be 100. And at negative 1, the value will be 10. So when we draw x, 10 to the negative x power, it's just like taking this curve and flipping it around, left and right. Now, let's add 1 to 10 to the minus x plus 1. It is already 100, so adding 1 doesn't change much up here. It's already a big number. At 10, we add 1, changes a little bit. Now, at 0, it becomes 2. And at 1, this is a small number, 1/10. So adding 1 to it is a significant change. It becomes 1.1. And at 2, it is 1/100th. So this is becoming closer to 1. When we draw this, it would be the same as this function for 1 plus 10 to the x, moved up 1. And for this, x 10 to the minus x plus 1, it'll be the same as 10 to the minus x, just moved up 1. Now if we divide 1 by this, we get a function that is close to 1 for negative numbers and close to 0 for positive numbers. And it has a smooth transition in between them. We'll soon see that this is a useful feature to build into functions that we want to construct. Changing this x to minus x just flips it left to right again. As we can see here, for negative 2, this is 1/100th, close to 0. And for larger numbers like 2, it's very close to 1. So at 0, we're transitioning from 0 up to 1. Now, let's plug this into the sine function. The sine 2 pi times x function, which when we go from 0 up to 1, it will go through a full cycle of the sine. So, when this function transitions from 0 up to 1 times 2 pi, it goes from 0 up to 2 pi. So it means near 0, it's going through one full cycle of the sine, and then leveling out near 0 away from there. If we don't have a negative on that x, then the function, this is the one we're using, this function transitions from 1 down to 0. So after multiplying that times 2 pi, it will transition from 2 pi down to 0. So this is going down first and then up. Otherwise it's the same as this, which makes sense because the only difference here is we've changed x to negative x. And as I said, that works for any function. Any function that you want to swap left and right, just change the x to a minus x. Okay, let's look at some examples using these. Now this function is going from 0 up to 1 at the point 0. So if we add 1 to it, it's going from 1 up to 2. So for negative numbers, this top envelope is nearly equal to 1, and then near 0 it transitions up to 2. So we draw the negative of this at negative 1 transitioning down to negative 2. This is the lower envelope, and then we just make the sine function oscillate between those two, where this function is nearly 1, then this looks like the normal sine function. And where it's 2, it's just becoming 2 times as big, going between negative 2 and positive 2. This time, we're going to add 1 to the flat top mesa function, which remember was nearly 1 between negative 1 and positive 1. So when we add 1 to it, between negative 1 and positive 1, it's going to be near 2. And outside of that region, it's almost exactly 1. We draw the negative of that for a lower envelope and make our sine function oscillate between those two envelopes, as usual. For the third example here, we've expanded a function horizontally. We've made it twice as wide. And we do that by first dividing the x by 2. This kind of change also works for any kind of function. Any kind of function you want to expand horizontally, just substitute x over 2 instead of x. If we want to make it 10 times wider, just have x over 10. So we put x over 2 into this function, x over 2 to the 10th power plus 1, and then divide 1 by that. And we get this kind of function. Between negative 2 and positive 2, this function will be almost exactly 1. And outside of that range, it falls to 0. So we multiply this times the sine. It means that we're putting the sine in between this function. So between negative 2 and positive 2, it goes through 2 nearly normal cycles of the sine. And then it dies off to 0 outside of that. At first, there'll be a slight rise here. It'll soon drop off to a very small number. Now we're going to define some functions and giving them names. And the main motivation for this is to get used to defining your own functions, which is very closely related to computer programming. When you make a computer program, you'll be making a lot of functions. And this is what we're doing here. We're making a new function and giving it a name. I chose the name p, that stands for positive. So for all the positive numbers, they're going to be unchanged. For all the negative numbers, they're going to be 0. So we can implement this with x plus the absolute value of x over 2. I have the 2 here because if we just have x plus the absolute value of x, then for positive numbers it's going to be 2x. And it's simpler to use a function that just does what you want, and what we want to do here is to make the negative numbers 0 without having any other side effects. If for the positive numbers we doubled it, well, that would be a side effect and we'd have to consider that whenever we want to use this function. So it's easier to use a function that doesn't have any other side effects. It just makes any negative number a 0. Because if the number is negative, the negative number here is just x, it's still negative, and this is a positive number. That's why it makes all the negative numbers 0. So we can make some changes on this. As we did before, moving that little hill function over to the right 4 units, this time we're going to take this function and move it to the right 1 unit. So in place of x, we put in x minus 1. So we have x minus 1 plus, now the absolute value of x minus 1 over 2. It'll look the same as this function, just moved over 1 unit. So it stays 0 until you get to positive 1, and then it starts growing in a straight line at 45 degrees. Now, if we take this function and subtract this function, until we get to 1, this function is still 0. So if we subtract this function from p of x, it's not going to change anything because this part is still 0. So between 0 and 1, this is going to leave x unchanged. It just goes up at a 45-degree angle. And then it levels off. It won't grow anymore after this point, because if we're above 1, this function starts growing, and this is growing also, but we're subtracting a larger number from this one, so it stops the growth. And we can move this function to the left by putting in x plus 1. Now it's going to look like this, and instead of starting to grow at 0, it's going to start to grow at negative 1. So at negative 1, it's 0 and starts growing. By the time it gets to 0, the height will be 1, and then forever after, it'll just continue in a straight line. Now this time, I'm going to start it growing at negative 1. So it's this function that starts to grow at negative 1, and then where I'm going to subtract p of x, it's going to stop it from growing at 0. So this function will be 0 until it gets to negative 1. Then between negative 1 and 0, it'll be a straight line, and for all the positive numbers, this will just be 1. P of x minus 1 minus p of x will give you this kind of shape. So let's think about some ways to use this. If you have sine pi of p of x, remember p of x, it just makes all the negative numbers 0. This will look like a normal sine function for all positive numbers. But for all negative numbers, it'll just be 0. Now, instead of p of x, we have p of x minus 1. Here's p of x minus 1, which starts to grow at 1, and it's 0 until we get to 1. So this function will be 0 until we get to 1, and then it starts to grow as usual. Now, because it's starting to grow at 1, it goes up at first. So between 1 and 2, it's going to be positive, going upwards, just like this function between 0 and 1 was going up. Now, if we subtract p of x minus 1 from p of x, that's what we did right here. So between 0 and 1, it grows as usual, and then it stops. So as you might expect, for all negative numbers, this is 0. For 0 to 1, this looks like a normal sine function, and then it stops growing. So it's going to be flat here. This was a mistake. This function will be exactly the shape of a sine function in this region, and exactly 0 outside of this region. And as an interesting way to change this function, Here we subtracted the function inside the sine argument. We could also do the sine on each one of these parts and then subtract it. So if we take this function, and I made a mistake here. Because this is positive and this is negative, then this should be adding a number. This right here. So sorry about that, folks. That should be adding. Because what we want to do this time is we want to add this function and this function. These functions are already the negative of each other. So because this is becoming negative here and this is positive here, they're going to exactly cancel out. So between 1 and 2, it's going to cancel out and be flat, and that's going to continue from now on. So this function with a plus here is going to give us the same shape as this function. No particular importance for memorizing this kind of identity. It's just an exercise in understanding shapes of functions. And I think that'll help you greatly in understanding engineering books. As another example, playing with the p function, if we start it growing at -1, and at 0 we subtract 2 times the p function. Then at -1 it'll start growing, and at 0 it will not only stop the growth, it will reverse the growth. So from 0 on, for all positive numbers, it's going to be decreasing. And to this function, if we stop the decrease at x equals 1, and we do that by adding this part, so we start the growth at -1, and at 0 we subtract 2 copies of the p function, which stops the growth at 0 and then makes it start declining at 0. And then this third term, p of x minus 1, is to start the growth, in other words, to cancel the decline at x equals 1. Now we have this little straight triangle that looks like a tent function. Okay, this S stands for step. This is a step function. And a real mathematician might start screaming and pulling out their hair when they see this, because it's actually undefined at 0. But I'm kind of sloppy about this here, and we'll just not worry about that one particular point. So for all negative numbers, it's 0. And for all positive numbers, it's 1. Now the reason for that is, without this x down here, this was growing just as if it was x. So for any positive number, this is equivalent to x divided by x. So that's the reason that for all positive numbers, it's 1. For 0, we'll just define that it's 0 or whatever you want. We can move this function to the left by substituting x plus 1 in this equation. And if we want to write it out, we can write it out this way. This just involves putting in x plus 1 wherever we see an x in this equation. But it's easier to just call this s of x plus 1. So it's a step function moved over 1 unit to the left. So for all numbers less than -1, it's 0. And for all numbers greater than -1, it's 1. Now we can make a real square mesa function instead of that round thing that we were doing before using the exponents. This will give us absolute sharp sides because we make it step up at -1 and then we make it step down at +1. The step function of x minus 1 is this same function moved over 1 unit to the right. So when we subtract this function from this one, it means after 1 it's all going to be 0. And by the way, in comparison with what we were doing before with the exponents, if we had a really big exponent here, like x to the 1000 power, it would look pretty much like this. The bigger the exponent here, it has a sharper and sharper transition. And this is infinitely sharp. Now, using the round-shouldered, flat-topped function before of 1 over x to the 10th plus 1, we can multiply that times x squared. And this will look pretty much like x squared until we get close to -1 and 1. And then it'll drop off towards 0 and rapidly approach a very small numbers for any x greater than 1 and any x less than -1. And then we can sharpen this up by using this definition, which is infinitely sharp, and multiplying that times x squared. So we have x squared times the step function moved to the left minus the step function moved to the right. So this looks just like x squared in the region from -1 to +1, and then it's 0 outside of that region. All right. If we take sine times this, then we have a perfect sine function between -1 and +1 and 0 outside of that region. Whereas what we were doing before was kind of rounded. This is the sine times the step function moved to the left. So we have this step function of x plus 1 multiplied times sine. So this looks like a normal sine after -1. So the normal sine just starts at 0 and goes up at first. So this will be the same as that. We're just multiplying it times the step function, which forces everything less than -1 to become 0. And here we're multiplying the normal sine function times the step function moved to the right. Now, the normal sine function, between 1 and 2, it's going to be going down. So this also is going to go down. So it's the same. And it just starts here and then continues as a normal sine function. This next thing that I'm doing is making the sine function grow twice as fast between 0 and 1. And the argument that we're putting into the sine function is given right here. And what this function does is all negative numbers are unchanged. Between 0 and 1, it grows twice as fast in a straight line. And then after that, it just grows at the normal rate of 45 degrees. Now we do this with x plus p of x, which starts the growth, and then we're subtracting the p of x minus 1, which stops the growth. And this is all being added to x. So we put this in here, and the effect is a normal sine function everywhere except it's going twice as fast in here. So we've got 2 cycles going in this region between 0 and 1. And then it continues as normal.